Hi everybody, this is the last phase of the height of the ceiling lab. We're going to take your measurements, calculations, and your uncertainty values and put it all together to come up with a final value for your predicted height. And then I'll give you what I measured the height directly to be, and then I'll talk to you about how to decide whether yours is the same as mine. At this point, you should have used this equation right here to calculate a height for the room based on the weight of the ball, the time it took to fall, the average time it took to fall, and its mass. So I'm going to put in a hypothetical value. All right, I'm going to put in, let's say I got a value of 3.15 meters. Okay, so we want to decide that's h. What we now have to figure out is what's our plus or minus value. In other words, delta H. What's the absolute uncertainty in our height? Is it, hopefully it's small. I'm going to guess ours isn't going to be because of the timing issues, but that's why I did all this, so we can work this all out. So I'm going to show you how to get this delta H, the absolute uncertainty. This is using those rules of propagation of error that you watched the tutorial on and hopefully did the practice before you come to this. I'm going to walk you through it. We'll come up with the value and show you what a final product should look like. I'll give you a chance in class to ask about anything before we formally upload this for a grade. Okay, so let's get to it. We have the equation then. H, I'm going to write it over here in the margin, equals f of g t squared all over 2m. So in order to find the absolute uncertainty in H, I first have to find the relative uncertainty, or the fractional uncertainty, delta H over H. We do that first. Once we get a number, then we can multiply it by the actual height to get the absolute uncertainty. So the rule for the uncertainty in H, the delta H over H, is conceptually, it's simply the sum, okay, of all the relative or fractional error or uncertainties in our measurements. In this lab, we have three measurements: weight, time, and mass. So we got to look at the fractional uncertainties of all those, add them up, and then we've got our first stage. So in terms of an actual equation, which I'm going to write down here, delta H over H, I'm going to add each term. So our first term is F, so I'm going to say delta F, I'm not going to put the little g there, over F, there's our fractional uncertainty of that, plus the time. Now, things get a little bit complicated time, but hopefully you understand this. Because it's squared, I bring that 2 out in front, twice delta t over t. And if you're still wondering, why don't I square the delta t over t, or why do I bring the 2 out front? Well, it's as simple as this. T squared is the same as t times t. So if I were to treat these separately, I would have a fractional uncertainty of delta t over t for this part, and then I would add to it delta t over t for that part. Well, that's just 2 delta t over t. So that's why we multiply by 2, because we use time twice. And then to finish this off, we have the mass, so plus delta m over m. Now some of you might be wondering, what about this 2? Well, the 2 doesn't factor into this equation because 2 is not a measurement. There's no uncertainty in it, so I don't put it in here. The 2 is already taken care of when I calculated H. All right, now I have to put in the values for each of these. So this often comes up, well, where do I get these values? Where do I get delta F? Where do I get F? Delta T, T, delta M over M? Well, I go back to my data table. So let's take so what I want you to do down here is put in the actual values, do some calculations in here and do that. So let's take one at a time. Let's start with the more difficult one and what's going to confuse you more, the time one. So in timing, we got to take 2 times delta t of average over t of average. Okay, so what do I mean by that? Let's go back to our data table. On your data table, you have 2 sources of uncertainty for time. You have instrument uncertainty, which we already said was 0.01 seconds because your stopwatch can go to 100th of a second. But since you did multiple trials, right, etc., you calculated a random error. You took your greatest value, subtracted your least value, and divided by 2. So let's say, hypothetically, I came up with a random error of 0.08 seconds. Okay, so my spread was about 0.16 seconds. So this is labeled as delta t average, whereas this is just labeled delta t to distinguish between the uncertainty due to the multiple trials versus the uncertainty due to the instrument itself. This number is almost always going to be bigger than that number. So this is the delta t we want to put in our uncertainty equation. And then our average itself, let's say your average time was, I'm going to guess, probably 0.62 or so. It's going to be around 0.6, maybe 0.5. Ideally, it's really closer to 0.7, but we won't worry about that right now. So there's my average. There's my uncertainty, the bigger of the two uncertainties. So I go back to the calculations, and I put in delta average, which I think was 0.08. And then I put into my average value, which I made up as 0.62. I divide these two, multiply by 2, and let's say I get a number. I don't know what number I'm going to get. Whatever. Let's say it's 0.15. Okay? In other words, I don't know time. I know time within 15%. So not really good, not awful, but it is what it is. So for the mass, I just have to do delta m over m. Well, to get the delta m, going back to the front, I get it from right here. So here is the mass value in kilograms. I want things in kilograms, and here is delta m. So I take whatever value of delta m is, I believe it was 0.0001 kilograms, a really tiny value, and then I put it over whatever mass I had, let's say 150 grams. I can see right away this is going to be a very small fractional uncertainty. In other words, I'm pretty certain, I'm pretty clear what the mass is. So let's say this is a really tiny number, 0.001. I do the same thing for weight. So weight is really just F, right? Okay, so I go here and I get the values. There is my F, here is my delta F. Okay, that might be a little bit bigger than the mass one. Let's say this comes out to be 0.0. So what I now do is, based on this equation here, I got to sum them all up. So I sum these all up, and it's essentially 0.16. All right, I'm just going to round there. Okay, so what I'm saying there, let's recall, this is delta h over h, my fractional uncertainty in height. In other words, I'm saying I know my height to within 16% of its actual value. That's what the 0.16 means. It doesn't mean 0.16 meters at this point. It's simply a fraction. So ultimately, I want to get the absolute uncertainty, delta h. So the general equation, the last step we have to do, is my delta h, the absolute uncertainty, is equal to my fractional uncertainty, delta h over h is how we designate it, times the height that we calculated already. So in my particular example, my delta h over h, I just found out to be 0.16. The height that I calculated, if you go back to the top, well, on the video, right, let me just reference it, I made up a number, 3.15. So I would take 0.16, multiply it by 0.315. In other words, I'm taking 16% of 3.15, punch it in the calculator, and I get 0.504 meters. So I'm saying my actual uncertainty in height is a half a meter. Out of 3 meters isn't very good. Okay, in other words, it's 16%. Now I can write my final value. And here's where the rounding finally comes into play. I know it's going to get confusing. It's kind of going back and forth. The first rule is once I get this value, I must round to 1 sig fig. So 1 sig fig is 0.5. So this now tells me how to round my height. If this uncertainty, delta h, is to the nearest tenth, then I must round my height to the nearest tenth. So I can't leave this as 3.15. I'm going to call that I'm going to round up to 3.2. And there's my final height. There's my final result. And what you're saying is I'm pretty darn certain that my height is somewhere between 3.2 minus 0.5, which is 2.7, and 3.2 plus 0.5, or 3.7. And so it's a pretty big range. But that's how you do it. Now, what is the actual height of the room based on how I measured it with the meter stick? I got 2.68 meters, and I would say plus or minus 0.02 meters. Okay, I'm going to give a little wiggle room. Maybe the ceiling is not perfectly uniform all over the place, so I'm pretty darn sure it falls between 2.66 and 2.68 0.70. So in this case, now I can ask myself, are these two values the same statistically? You say, well, no, they're not. 3.2 is not the same as 2.68. But we got to take into account the uncertainties in both. So that's what this last question is about. Is there significant overlap between the two? And this is how you would look at it. And it's a judgment call, but that's okay. We're just learning this. So if I take my value, I'm saying it's somewhere between 2.7 and 3.7. All right, I just added and subtracted 0.5 from my value. The actual one is somewhere between 2.66 and 2.70. So the question is there much overlap between these two? And the answer is no, right? So mine is barely on the edge of that, and then it goes way above. So I would say it's not statistically the same. And the reason for this is, and I go back to my error and say, oh, here was my major source. It was my timing. I had a huge range in timing, or maybe my average time was well below what it should be. Those are things you want to discuss and go back. Okay, so good luck with that. Ask questions as they come up. We'll talk about this in class before I have you upload it for a final grade.